Thank you for joining us, the Virtual Foundry's webinar about debinding and sintering filament today. And true to form, I need to tell you that we are in southern Wisconsin and still very much in the grips of winter. It is a very chilly 5 degrees Fahrenheit. That's minus 15 for you Celsius users. And one of my favorite things about this work is working with people from all over the world. So I do see some snow on someone's camera. I'm right there with you, Steve. So if you're in some place more interesting than southern Wisconsin, tell me your location and temperature in the chat. I do see already it's 80 degrees in Florida. Lovely. So we are going to get right to it. So what you're seeing on the screen right now is our agenda for today. So we'll do a couple of introductions for your presenters. We're going to talk through sintering basics. What is this even about? How does part design play into the process? What kind of shrinkage can you expect? What are the mechanical properties at the end of it? What's the process like? And we'll have some demonstrations by Brad. And we do also have a couple of special guests today, which I'm very excited about. And as I said, we'll also have some time for Q&A. So as we go through, again, please type your questions in the chat box and we'll capture all of those as we go through and either answer them in line or at that Q&A section. So let's get right to it. As I said, I am Tricia, president of the Virtual Foundry. Presenting with me today is Brad Woods. He's our founder, CEO. He's the person who invented filament and the filament process. He handles everything science. I handle everything business. That partnership works great for both of us. And our special guests today are Matthew Drummond from the University of Guelph in Canada, and Mister Highball, a hobbyist who's been working with filament and posting lots of really fun videos on his YouTube channel about that. So we'll hear from both of them later. The webinar is being recorded, so if you miss anything, don't worry. It will be posted to our YouTube channel, and I'll send a link to everyone who registered when that video is ready, so you won't miss a beat. So let's get to it. Sintering basics. We're going to hear a lot from Brad today. So Brad, why don't you come on and say hello and walk us through the basics of sintering. What is this all about?
Okay, so we're going to talk about sintering. So essentially, sintering is the science that lets many small particles start to behave as a large single object. And everyone has dealt with sintering, whether you realize it or not. It's the core of how all ceramics work. So all the way down to pottery, things like that. It's likely that everyone has some type of interaction with the process of sintering. In pottery, it tends to be aluminum oxide, so Al2O3. And the same principle applies to metal. And our parts, essentially, our material is metal powder that's held together with a thermopolymer. Just enough to keep it into the shape of a filament and just strong enough that you can handle it, get it through your 3D printer and 3D print a part. So after you've printed the part, it's heated to remove the thermopolymer and then heated further until the particles weld together. And this is a very interesting process. It's actually a property of surface tension, so atomic diffusion. It gets really interesting, very complex, but it doesn't need to be complex. So we've developed solutions that simplify the process. In fact, the sintering process that I will demonstrate for you today, the heat side of it, the debinding side of it, and the sintering side of it, each only has 2 steps to it: a ramp and a hold, and that's it. So things are becoming much easier as we go along. As we gain experience, we find better methods of doing this. We're getting higher quality parts. And yeah, what else should I talk about, Tricia?
Brad, we should mention that this debinding happens only thermally. So all you need is heat And the debind and the sintering process can happen in standard regular kiln equipment. So your kiln needs to be able to be programmed. That's very important, so you don't have to manually manage the time and temperature changes. And it also needs to be able to hold the sintering temperature of the material that you're working with for several hours. That's it. So those are the two requirements of your kiln. What you'll see in Brad's demonstration today is the kiln that we like to use around here. We do also have that available for sale. So you'll get a look at that as he goes through the demonstration, but any kiln will work.
One topic to bring up is that oxygen is the enemy of heated metal. Heated metal tends to react with any oxygen that's present, and it becomes an oxide of that metal, which is something we absolutely do not want in the metal sintering process. So to combat this, in a large-scale $1 million industrial kiln, they would either vacuum out the atmosphere or they would fill it in with an inert gas like nitrogen or argon or whatever is appropriate for the metal that they're working with. We get around this process by adding carbon to the sintering environment. When it gets to the right temperature, any present oxygen will react with the carbon, it'll become CO2 and can no longer react with the metal. So this is how we deal with oxygen in our sintering process. It's very simple and elegant and interesting.
Yes, thanks, Brad. And I know that you're going to be walking us through that as well, and we'll talk more about that oxygen prevention. But let's also mention that what Brad is talking about with that oxidation and the danger of oxygen getting to the part applies to the metals. We do offer ceramic and glass materials that are not subject to that oxidation. And in fact, some materials actually prefer oxygen during the sintering process.
Right. Our ceramic material actually contains aluminum oxide. So giving it more oxygen has no effect on the process.
And then let's talk about how part placement in the kiln affects the process. This is something that always surprises me about how particular the inside of a kiln can be.
Right. The inside of your kiln has, probably 9 points that have very different temperatures. Each of the corners are a different temperature, and the center is its own temperature. So as I've been doing research here, I'll actually put in data monitors and record all that data just to see what's happening and where. And what we've come to understand is that the placement of the crucible in the kiln is crucial. And beyond that, the position of the part inside of the crucible also has a pretty dramatic effect on the temperatures. And when you start dealing with temperatures that get up in the area of, over 1,000 C or, somewhere in the area of 1,600 F, it becomes difficult to keep all that energy in one place and keep the temperature high. So the second you remove energy, it wants to cool down, and it does it rapidly. So what we want in the sintering process is a gradual increase in the temperature that is stable, and then a holding at a temperature that is stable. So the caveat to my positioning observation is that once you identify the correct place, you get a consistent result. So you can perform the same activity over and over many times. So it can be a challenge to get the first successful sinter. But once you identify a process, it's easily repeatable.
So we've talked about one variable of the process, and that is the part placement in the kiln. Let's talk about some more. So, and that's going to be in the part design and how the part design itself affects the rest of the process. So we're talking about wall thicknesses, infill, overlapping layers. Brad, the first question I want to ask is it okay for the part to have different thicknesses within the same part, like the piece in the upper leftmost part does in this picture?
My answer to every question is never yes or no. So the answer to this question is the more variation you have between very thick and very thin parts, the more difficult it is to get a successful outcome. And the image on the screen there is a very good example of a method of optimizing additive manufacturing parts for the printing process itself. So yeah, you could succeed with the part on the far left, but it would be much easier if you focus on a part that is
So as we see more and more parts move to generative design to accommodate for this new method of manufacturing parts, the process becomes even more simplified. Brad, talk us through infill and overlapping layers and how your print settings can impact the sintering process.
Right. This is something that we're discovering. So as you're printing this, the polymer with the thermopolymer and the metal together, an interesting thing happens when you try to force a large group of spherical particles through a single space. That is that the larger particles get pushed to the center. So each print line winds up having more large particles at the center of the print line than it does at the edges. And this normally, I mean, this isn't generally a big problem unless those lines don't slightly overlap. What'll happen is if they don't overlap slightly, they'll start to delaminate during the debinding process.
And how much infill do you recommend for different parts?
We've done parts that are essentially hollow. The technique that we use, so there's some people in Italy that do busts and things like that. And in our sintering process, I think everyone here is going to be somewhat familiar with it, but we sinter in a ballast. So we bury it in a powder. That's what provides the support during the sintering process. So when you have a situation where the object is open, you can just put the ballast inside of the part. So like if you picture a baseball with a hole in it, it's an easy example. In those types of strategies, you can go with no infill at all. Beyond that, we typically tell people start at about 40 to 50%. And again, this depends on your part shape. Do you have large solid bodies? Are they all thin? And it's highly dependent on the part, which is part of what makes this such a difficult question to answer.
Right. I know the answer to a lot of questions are in the engineering sphere are it depends, and that applies here as well. So let's move on to a shrinkage discussion. I know this is on the minds of many people when they're figuring out how to slide or how to start with their computer model. So walk us through the association between shrinkage, density, and part shape change potential.
Right. So on our side of things, when we make this filament, it's our goal to get as much of the additive into it as we can. So let's stick with copper. So in the example of copper filament, we want to get as much metal in there as possible and as little plastic as possible. In the end, the idea is to remove the plastic. So if you have too much plastic and too little copper, you'll wind up with voids and that kind of thing. So essentially what we've done is our recipe and our material loadings are very, very specific. I mean, all the way down to the particle size, shape, and the blend of the particle shapes. We've designed this so they all fit together very, very well. And so when you take, for example, a copper part and you debind it and you remove that plastic, there's space where the plastic used to be. So something has to happen. Something has to occupy that space or it just fall apart. And what happens is during the debind phase, the part will shrink somewhere in the area of 3%, 2 to 3%. At that point, you have a part that is made up of particles that are all touching one another. And there's a little bit of a little bit of binder remaining, just enough that you can handle it in the brown state. From there, the next step is to sinter it. So here's where you put it in the kiln, and you'll run it up to about 90% of the melting point. You never get to the melting point, that would obviously destroy it. So a good sintering temperature is between 80 and 90% of the melting point. And what happens is the particles, first they become kind of sticky and they contact each other. And then through a process called atomic diffusion, which is essentially just surface tension. It's the same thing, like you see two water droplets connect to each other. The same thing is happening but with metal. And the parts connect. And at that point, you still have porosity. You have gaps between the particles where it's not connected. At this point, the part has shrunk about 7.5%. And in many cases, our users just leave it here. This is okay. Other users need to have a very, very dense part. So you simply continue to debind it. The particles, they don't melt, they diffuse further, and the part shrinks more and more. So by the time you hit about shrinkage of about 20%, your part is about 98% dense.
So the more you shrink the part to get to that 20% shrinkage, to get to that higher density, the more potential there is for that part shape to change. And that's when loading it into the crucible becomes very important, and how you get that part supported in the crucible.
Right. And this is kind of one of the advantages of our materials. You have complete control over the process. Other solutions will limit your options to force you to have a positive outcome. Go ahead.
When we talk about that, the shrinkage being material load dependent, when you follow the instructions that we have posted on our website, the bronze and copper are going to be around 5 to 10%. The steels are going to be a little bit more, because a little bit more shrink with the instructions on our website, because they have a little bit lower material loading. And the ceramics, especially the 46D ceramic clay, has a much lower material loading by mass. So that one's going to shrink a lot more. And that's going to be more like 40% following the instructions on our website. And when we're looking at part thickness, if you have a part like we looked at on the last slide, where some of the part is thicker and some of the part is thinner, how are those two areas of that part going to shrink at the same rate? And what about that X and Y and Z axis?
They'll shrink the same amount. The problem actually comes in as you just start to enter the temperatures where the particles start to sinter. In the end, they will have shrunk by the same amount. The problem is they may shrink at a slightly different rate over time, which can lead to cracking and more distortion. The solution to this problem is to just move very slowly through this point in the heat ramp.
So you talked about time and temperature adjustments in order to affect the shrink rate. So you can shrink it a smaller amount by holding it for a shorter time. You can shrink it more by holding it for a longer time. So when we talk about the potential for part shape change, metal 3D printing for a part that needs a tight tolerance or has tight tolerances should be considered a near net shape activity. So you're getting a part that can go through some final machining, finishing, or whatever else you need to do to it to get to those tolerances. So let's talk through mechanical properties. We know that the final parts do have some porosity, as you just explained to us. And so we know that the final parts here are going to be a little bit different from cast or machined. So Brad, talk us through that. How is that going to be different?
Right. Everyone's first question when they find our materials in our process is how does it compare to casting and casting and machining. And it's not so simple to answer. Much of the straight answer would be if I tried to make a block of metal that's machined and a 3D printed block of metal that's machined or that is 3D printed, the machine part would be stronger and more suitable. The better answer is that you wouldn't want to additively manufacture a simple block. There just isn't a good way. It doesn't make sense. So part of the additive manufacturing revolution that we're coming into here is getting people to think about part design a little bit differently. Parts need to be designed with additive manufacturing in mind. When that's the case, parts can outperform other categories. This is a well-known issue in like the people that develop the standards like ASTM and NIST and people like that are actually looking at our materials and trying to figure out how to quantify the properties of a properly executed additively manufactured part. And the best answer I can give, it's not a depends, but it's different. It's just a different thing. You're not going to try to additively manufacture a trail hinge. It just wouldn't make sense. But where the applications are appropriate, additive manufacturing can outperform casting and machining.
And then when we get into the conductivity discussion, especially with electrical conductivity, if we're thinking about copper, because those final parts are porous, they are going to have reduced electrical conductivity compared to a solid block of copper, for example.
Right. We have a student's thesis paper on our website that went through and did a careful analysis of thermal conductivity of our copper, better than bronze tube. I think it's just copper. Basically, we found is that the electrical conductivity of the copper is dependent on two things. Number one, purity, but number two is density. So a highly porous part, say it's only 75%, 75% metal, it's filled with holes, sort of like it's a sponge, will conduct electricity at roughly 75% the rate of pure copper. And we have two types of users. We have people that want conductivity, and we have people that want dielectricity. They want the best insulators you can possibly make. So this is actually the conductivity part of additive manufacturing is becoming a bigger and bigger topic, and people are getting further and further into it. It's becoming more and more complex, and it gets more and more interesting. My expectation is that we'll develop some additive manufacturing alloys that work better for the additive manufacturing process, like they would have silver in them or something like that. And the big one is graphene. It'll probably wind up the additively manufactured, highly conductive materials. That's just highly conductive. Will likely become some form of copper and graphene.
So yeah, right on. Development continues. That was a great lead into the second topic here. So as we talk about material load considerations, there's a consistent effort to increase the amount of material that can be loaded into that plastic binder. And there are always incremental improvements there. And the second is liquid phase sintering. We're going to hear a little bit more about that later from our guest, Mr. Highball, because he uses this technique frequently. Liquid phase sintering involves the introduction of a complementary lower melting temperature metal in the sintering process. And that complementary metal will melt before your primary part sinters, so that molten metal then gets sucked up into your primary part, infiltrating all those pores that were left there, creating an essentially solid part with virtually no shape change. So this process has been worked with. It's not finalized, so development continues in that area as well.
Yeah, I actually consider this to be the most, not the most, but a very interesting area that more time needs to be spent on. It's a way of mitigating the porosity problem without having to deal with large changes morphologically.
All right, let's get on to the process. So when you're thinking about debinding and sintering filament, two things need to happen. The first is that the part shape is supported, and the second is that oxygen is prevented from reaching the part, and I'm talking about metals in that case. So we solve the part shape problem by using a refractory ballast, and we solve the oxygen problem by using sintering carbon. Some people like to use a gas fill kiln. In that case, that takes the place of the sintering carbon, but in an open atmosphere kiln, sintering carbon will prevent that oxygen from reaching your part. The ballast is reusable. The sintering carbon is designed to get consumed, so that can be filtered and you can reuse the part that remains, but that is designed to be used up in the process. So that's a consumable item. You're going to bury your part, and Brad will show us this in a minute. You're going to bury your part in that refractory ballast, making sure that all of the part features are supported. You're going to tap that ballast in there, not pack it heavily. So that part still needs to be able to move and shift as it shrinks on itself. So it's important that it's supported, but can also move. And then once all of that is loaded, you'll apply the sintering carbon to the top of that. When the sintering carbon is applied is dependent on the material that you're working with. So sintering carbon is applied after the debind is completed for copper and bronze. Sintering carbon is applied at the very beginning of the process for steel. And then there's no need for that sintering carbon for ceramic and glass, since they are not so sensitive to oxygen. So let's look at exactly what you need for each material. Copper and bronze, you're going to use an Al2O3 or a talc and sintering carbon. Steels, that ballast material is going to be the Sapphire 3D steel blend and sintering carbon for the oxygen. For ceramic and glass, you'll just need that ballast material, the Al2O3 or the talc. So Brad, talk to us about the difference between the Al2O3 and the talc, both of which we offer as your sintering supplies.
So the Al2O3 is large particles, so it's about 100 mesh. So it's sort of like beach sand, a little bit finer than beach sand. And its job is to support the part, and it actually, and we will put it into the crucible and shake it in there, and it'll settle all around the part and keep it in place. And it does a few different jobs. It partially helps wick away the gases that are being removed during the debind process. And it's kind of interesting. After that, we now recommend that people do the sintering in a two-step process. So they'll set up, bury the part in Al2O3, and debind it. As a secondary process, they'll take the brown part out of the Al2O3 ballast, and it's still strong enough to handle. It's a brown part. It would break if you dropped it, but it's plenty strong enough to handle, and you can actually manipulate it if you want or sand out of it. Step two is to put it into the talc, and this is just plain old volcanic talc. There's nothing special about it. The reason it works well is it's very powdery and fluffy, so it will yield as your part needs to change size as it shrinks and densifies. It moves out of the way easily, so it provides support at the point where it needs it, but it is able to get out of the way as the part needs to change its shape slightly during the densification part of the sintering process.
All right, let's get right to those demonstrations. So I'm gonna stop share. And then we will make Brad nice and big. He's going to switch his screen over to a secondary camera so he can show you a demonstration of loading the kiln and, I'm sorry, loading the crucible and putting that into the kiln.
Okay, so for step one, this is the AL203. So all we do, take a crucible, fill it about halfway up. Set the green part on top of what you've already put in there. Add a little bit more. I like to shake it around so it settles in nice. Make sure there's no air gaps left. If your print has bridging in it, you want to give it an opportunity for the L203 to get under it. And that's where this happens. Then continue to bury it. You want the part completely covered about a ½ inch down from the top of the AL203. Yeah, let's put a little more in there. Looks kind of like this. I'll see if I can show you without spilling it. Not sure if you can see that on camera, but it's about 3/4 of an inch down from the top. Next step is to put it in the kiln and execute the debind program for copper in this case. And we've greatly simplified the debind, the recipe, we call it. So essentially, you're just warming the temperature up to about 400 degrees as fast as you want. And then over however many hours it takes, raise it to the sintering temperature at a rate of 100 degrees Fahrenheit per hour. So this is not a fast process, but it works really, really consistently, and you will get a successful result. So the next step so this is the next day usually. I run these overnight and then I'll pick up the next day. So the next day I will take just a household sieve. And you have a brown part. So this is a brown part. You really can't see on the camera. I'll post some pictures. I have some better photos with my big camera that we'll share somewhere so that people can look at them later. But there's minimal shrinkage. Like I said, at this point, there's maybe 3 to 5% shrinkage at most. Next step. Use the same crucible, and this is talc. And what makes it interesting is that it's so fluffy. I mean, it's been used as body powder for hundreds of years. So that's the whole idea. It yields easily. So when I push on it, it'll move out of the way as it needs to. So in this example, I'll fill this about 1.5 inches down from the top, settle it a little bit. I'll take my brown part, put it down into the talc. It pushes easily, the whole thing yields, move it around and make sure all the voids are filled. Put a little bit more on top of it.
Now, Brad, how fragile is that brown part? You're handling it in between the debind and the sinter process.
It's my best answer is it's way stronger than you'd think. You can actually sand on it and clean up the part if you need to. If there's something you don't like about it, it's easily manipulable at that point. If you drop it, it'll break. I would say it's similar to ceramic greenware or clay, somewhere in there, where it's easy to handle, but still fragile. So on top of the talc, we'll get that settled in there and top it off with sintering carbon.
Now, you really can't use too much sintering carbon.
No.
Whatever is left over at the end of the process, you can filter out and reuse again.
Right. And the best way to conserve this stuff is it will all be there except what has been exposed to oxygen and got consumed. So to maximize your efficiency on the carbon is to use There it is. Cover it. This is stainless steel foil they use for heat. They use it in heat treating a lot. So if you cover it like that, you can actually use almost no carbon, and you can sinter it back out at the end. So we put it back in the kiln for the sintering process, and this is similar. We ramp at a rate of 200 degrees per hour up to the sintering temperature. And that's it. There are no ramp and hold, none of that. We've simplified the process dramatically. Clean up a little bit here. So in the next step, this will be, again, the next day. So this is a multi-day process. We'll take it out, we'll take this off, and they take the stainless steel takes some abuse. It actually eats some of the oxygen, so it works as a getter, a sacrificial getter for you. So it'll look like this when you're done. And sometimes you can reuse these, often you can't. We'll make a new one. We'll take the crucible out. In the same way, just dump it into a sieve so we can find our part and fish out your brown part, or your sintered part. And it'll pretty much look like this.
Brad, how do you know that your sintering carbon was used up? What does it look like at the end?
If it's there, it wasn't used. If it's black, sometimes it'll get a little bit of yellowing to it, but pretty much as it's consumed, it becomes a gas. So it's just gone. So this is our sintered final part. And the next step is cleaning it up a little bit. This is a part. We need a better picture, but this is with about 10 minutes of work with a wire brush on a Dremel tool. I'll switch to my other camera. You can see it a little bit better. So this is what it looks like coming out. So let me show you that right now. So this is, okay, so this is fresh out of the kiln, a freshly sintered part. The bottom of it, I have hit with the wire brush. So there are no 3D printing processes where metals come out shiny and perfect at the end. There's always some post-processing of some type. And you can get to this easily with, like I said, just a wire brush, like not a bench grinder or whatever. You have a flex shaft or a Dremel tool works great, whatever it takes.
How is steel process different from the copper process?
Yes. Okay, let me switch cameras again here.
And what you just showed us is for copper. Does that also apply to bronze?
It applies to bronze, and it'll also work with glass and ceramic. The only difference being that you don't need the carbon for those two materials. So the steel blend looks a little bit different. So the AL203 is blended with graphite. So it looks a little different. It's much messier, but serves exactly the same purpose. So we would go through the same process here. We would put our part in. We fill it the rest of the way up. We put some sintering carbon on top of that. Cover it a little more lightly. We want the gases to be able to escape easily. So you can cover it like that, and it'll save you some of the some carbon. But otherwise, it's the same process.
This is more of a one-step process. You're loading the kiln completely, including the sintering carbon. The crucible, before you put the crucible into the kiln. Then once that goes into the kiln, you're running the debind and sintering cycle as one sort of programmed time and temperature profile. So the steels are going to work as more of a single process. Copper and bronze are working as a sort of two day or two separate step, debind, do some stuff to it, then sinter. And then you had said that the Pyrex is going to work more like the copper and bronze. You're going to do that 2-day step with it, except the only difference being you don't need the sintering carbon. Now, we do have some materials, if you've been on our website, that say they've been untested. And a couple of the ones that we get asked about most frequently are titanium and aluminum. So because of titanium's reactivity, we haven't tested that for ourselves. And also titanium really loves oxygen. So what we've learned is that the type of kiln that's gonna work well for sintering titanium is an all metal kiln, because titanium will also suck the oxygen out of a standard kiln's fire brick. And aluminum is also much trickier. Aluminum particles are each covered with an oxide layer that needs to be removed before those aluminum particles can sinter together. So that requires a specialized environment, including pure nitrogen, very dry with a vacuum. So we have a little bit of information then about that we can share with you if you ask, but we don't have the knowledge nor the equipment to be able to sinter aluminum. So that's why you see untested by those materials on our website.
And we have,
oh, sorry, go ahead.
sorry, we have partners in industry that have successfully sintered this, and they are working on it. So we hope to bring them on as a service bureau that people can send their parts to. I'm not sure if we can get to a place where people are sintering aluminum and titanium at home. Maybe I will keep trying. We're not there yet.
Other materials that you see that are listed as untested are because they sinter at higher temperatures than we have the equipment, or we don't have equipment capable of reaching those temperatures. So now I'm going to introduce to you our guest, Matthew Drummond from the University of Guelph in Canada. I can imagine it's not any warmer for him in Canada than it is here for us. Matthew, welcome to the webinar. Tell us what you've been up to.
Hello, hello. It's a little bit warmer. It's only 19 Fahrenheit, which has been was warmer
nice.
than last week when it was minus 27 Fahrenheit. So it's been a nice change of pace. Hello, everybody. I'm Matthew Drummond. I go to the University of Guelph in Ontario, Canada. I just finished my bachelor's in mechanical engineering at the university, and I'm going back for my master's of applied science. My thesis is FDM printing high carbon. I'm working with a corporate sponsor, and so we're doing a custom filament as well as my thesis, which is going to be the high carbon iron filament. I'm part of an advanced manufacturing lab at the university, and we're working with 3 types of additive manufacturing. FDM, which is my portion. One group is working on SLS, selective laser sintering for metal, which is powderized metal. Laser sinters it and you get a part. And then we have a binder jetting system. I can tell you it's very nice using FDM. They have a lot of problems, and the setup for it is thousands and thousands of dollars. One of our systems is across Canada right now, so we have to fly people out whenever they need to work and fix any issues. So it's quite nice having metal 3D printing at home, and currently right beside me in my student house. So currently I'm testing, the way I'm doing my testing is I'm testing this little, I don't know if you can see the little flow rate cubes. I 3D print these cubes with the highest infill and the highest flow rate that the printer will put out, and that will increase the density of the part. From there, I put it in a furnace. I can tell you right now, I'm using a furnace that's not programmable. Please get a programmable furnace. It takes a very long time and way too much time to use a not programmable one. I was there for 16 hours yesterday, and that was just for sintering. I debinded the previous day. So that's one nice thing with the high carbon is I debinded the day before. I left it all in the crucible. I replaced the carbon on the top, and then just put it back in, and then slowly warmed it up again, but then just put it right to the sintering temperature and sintered it. And I got pretty good results yesterday. So yesterday I did about 1200 Celsius, which is about 2200 Fahrenheit, I believe. I did that for 3 hours with these I did 4 flow rate cubes in there, and they turned out very well. I've tried previously, for the custom high carbon iron, I did a very slow cool down. So I got to the sintering temperature I used the steel debinding process. And then I got to the sintering temperature, left for about 3 or 4 hours. And then I just turned the furnace off, and I came back in the morning. It was still fairly warm, and I just left it for pretty much the rest of the day. And it just was nice and cool. And then last night I did more of a rapid cool down. Once it got to the sintering temperature, I turned it off, left it for about an hour, let everything kind of settle a little bit. And then I opened it up, and I had about 1/2 inch gap between the door, and I let kind of the air come out. And I got some very good results of my parts. As you can see in the picture here, those are the 3 microstructure we're looking at. As far as the research goes, we're trying to essentially make the strongest part as possible, which is why we have increased the density of the print itself as much as possible by increasing the flow rate. And then we're trying to get the austenite on the left side. And so if you can go to the next slide. So this is from my first sintering. You can see in the bottom left photo, we have those close lines, and that's actually carbon. We use acid etching, which is like a citric acid, which will eat away the top layer of the iron. You can see the carbon. And so you see those lines, that's the perlite. It's a fairly strong microstructure, and it's good to see. But I had very big trouble with keeping the carbon in the actual part. I'm using a very small crucible and a very small furnace right now. So the amount of space for these flow rate cubes is not that much. And the amount of carbon we can put on the top is very limited as well. And so I think in the next slide, you'll see the crucible has all the carbon is gone. As you can see on the left there, all the carbon is eaten away. And that's just essentially the remnants after it's all been oxidized. And what's actually happening from the high carbon iron, which I noticed in the microstructures on the right there, is it's very opaque around, you see the little carbon microstructure, but it's very opaque around it. And that's actually because the carbon from the part has been evaporated out through the steel ballast and has been taken into the oxygen. And so something to combat that is to, get a bigger crucible, put more sintering carbon in it, or we even were suggesting putting just almost another crucible in behind it of just carbon. And that would allow the furnace and the oxygen in the furnace to essentially eat away at that carbon before it goes in and takes the carbon from your part. And so we're trying to keep as much carbon as possible within the part. The austenite structure is the strongest you can get. It's the strongest you can find in steels, but it takes a lot of carbon to get that microstructure. And so keeping as much carbon as possible within your part is essential for a very high strength steel. The next test we're doing at the lab, and kind of my next test, is I'm going to print these flow rate cubes, and I'm going to increase the size ever so slightly. I'm going to make 5 or 10 or more, and then I'm going to run that standard debind and sintering program. I'm going to see at what size cube will it not fully sinter, and that kind of shows how much heat is getting into your crucible, and at what point, like how long you can sinter something, and then let it how am I trying to explain this? How much heat you can put in over a certain amount of time, and it'll fully sinter essentially. So I would set them all for 2 hours, and then see at what flow rate cube does not sinter fully after 2 hours. And it's a good way of seeing, like, within your furnace, and it kind of varies furnace to furnace, is how much power is going into it and how long you need to put it in there to fully sinter any cross-sectional area that's like the largest part. I noticed with the crucible before on my sintering process, that actually one side of the crucible had not all the carbon eaten away, and one side was like that beige you see there. And that's because part of the crucible was right under the coil. And so one side of the crucible is getting very hot just right underneath the coil, and the other side of the crucible is a lot less because there's no coil there and the carbon isn't being eaten as much. So it is something you got to look at, and I think the thermocouples within the part or within the crucible itself is a very good indication and a very good method to see which kind of what's going on within the crucible. And these are it's kind of rusty now, but I polished a couple samples, and you'll even see there is one sample is smaller than the other, and that the sample that blurred there, one sample that was closest to the side that was really burnt, like really sintered and underneath the coil, that's actually the smaller part. So that was something I noticed, was the parts that were closer to the coil and closer to that hotter side did shrink more. I'm not sure if I've got another slide there or not, Tricia.
Yeah, no, those are all the photos.
Okay. So yeah, that's pretty much it for me. I'm doing more of the research side. It's been very interesting. We have a lot of problems and a lot of kind of fun things to figure out. But the custom filament has been very nice, and the actual high carbon has been very nice to print with. The results have been very good, and I think it's about getting like a process to optimize it. I know our next steps are heat treatment. Once we get a good solid part, we're going to put it back in the furnace, get up to 400 to 800, and temper it in oil or temper it in water, and see what kind of microstructure we can get. I think the biggest thing with the high carbon is the carbon loss, and there's lots of ways to combat that, but it's just an interesting
Matthew,
process. Yep.
when you're talking about carbon content, what carbon content are you talking about? In the actual material itself?
Yeah, so it's actually as you can see in this microstructure in the middle there, the darker spots are actually, that is carbon. You want carbon content within the material, you want it bonded within the iron itself, and that's going to increase the strength of your part. The more carbon you have in the part, the stronger it will be. And like a lot of high carbon steels are very, very strong steels. And so the higher temperatures you get, the more that carbon inside gets eaten away. And then you are not able to create the microstructure and the strength you want, because the carbon's not there to be able to bond correctly.
Thank you for talking us through all of that. As Matthew's been saying, he's working with our standard stock high carbon iron filament, and he's also working with a custom iron filament that he asked us to make for him. So if you're thinking about a material that we don't carry in stock, we can likely make it for you. So talk to us about that to learn about that. Thank you very much for joining us and sharing your experience, Matthew.
Thank you for having me.
Matthew.
Next, we're going to hear from Mr. Highball, who is a hobbyist. He's got a bunch of fun equipment at home. He's been working on a lot of different techniques, including liquid phase sintering with copper and zinc paste, as well as some interesting finishing techniques. So Highball, come on and tell us what you are up to.
Hey, yeah, can you hear me okay?
Yes.
Cool. Yeah, like Tricia was saying, really just a guy in his workshop who likes the process. Been following the Virtual Foundry for a while when they kind of first started out, and I always like to reference, that there's really not another way to do this at home for less than like $100,000. So I always like to point that out to people, and it's a lot of people don't quite understand that's possible. So that's one of the things that really motivated me to really just go into it. And a lot of the stuff that I've done was just trying to understand how this material works, and mainly I've been focusing on copper, but I have also been experimenting with the other filaments. When Brad said and Tricia was saying that aluminum is not tested, well, I did test it. It just didn't work. So I have some other ideas on that. I think I'm going to keep trying, as Brad said, to see if I can get this to work at my house, just out of brute force willpower. We'll see if that comes to any fruition. But the parts you see here, well, first I'll explain a little bit about my setup. I kind of took this as a dive in, kind of head first approach with how can I do this in a way that I kind of want to go about it. So for me to learn something, I need to really understand the mechanics. I need to understand the downsides. I need to understand the upsides. And I really just have to fumble through it. So a lot of my sintering steps are probably a little non-standard compared to what's on the website, and that's just because I found something that kind of works for me. Use the sintering temps as sort of starting points, and the ballast materials as sort of starting points. But I have a little bit of a custom blend for my ballast. I do everything for copper in a one-step debind sinter, and my crucibles are homemade, where I've poured them because I wanted to maximize my kiln volume space. So I used a castable refractory for all of my crucibles to take up most of my kiln space, so that I can make kind of large parts. And the kiln itself is just an Olympic kiln that I had, I think, made to order. But all in all, for my whole setup, about, including the 3D printer, less than 2,000 USD, which is, I'd say, pretty reasonable for, making metal with a printer. So the few things that I have listed here, I've done some large parts, and I've done what I consider large, and I've also done some small parts. So one on the left is a recent no mask, which I've designed and printed and then sintered, and experimented with a little bit of a different patina techniques, including heat treat in peanut oil, and trying to do a little bit of green patina with the with some acid and salt. And then on the right, I've done small pieces, including little minis for tabletop games. So, which I actually have here, and the difference is pretty drastic. And for the detail that I was able to achieve on just an FDM printer, and then after sinter, there's really no deformities here or anything like that, and you get this really nice patina. You probably can't see it on the camera, but very happy with the small piece. And then I've done large pieces about the size of my hand, and solid copper. Yeah, it's actually there on the next slide there too. And I've experimented with like I said, different patinas for the copper. Copper is an interesting metal aesthetically, because you can make it, red copper, you can make blue copper, you can make green copper. I get the grungy, and I really like the burnt look for what I'm going with a lot of my pieces. This could totally be cleaned up with maybe like an HCl acid bath or something like that. But for the aesthetic of it, of a wall piece, it's kind of nice to have some of that grunge look to it, which yeah, so there's really, that's one of the reasons why I've picked the copper as a starting point. But I've also done the Pyrex, and I don't have pictures of that. Really like the Pyrex material because of just how easy it is to get a really good looking ceramic piece at the end. And experimenting, it's in the works, but experimenting with potential glazes, which can be applied to that as well. I'm not an artist by trade, so some of what I consider something that looks good may not be. It's in the eye of the beholder, is what I'm saying. But I think the possibilities of taking an engineering tool and mixing that into the realm of like art, if you will, leads to some pretty interesting results. And then taking that same single tool set and actually making something functional and useful in a production environment, that's also, pretty interesting, because I have done I've done casting as well, and in my opinion, it's a lengthier process that leads to a lot of cleanup at the end, and a messy workshop with the plaster. As Tricia mentioned, I do have some of my experiments have been kind of using with a custom blended zinc paste, I guess putty, if you will, think Play-Doh consistency. And I have applied that to some cube tests with the copper and was able to gain, to have a net gain in mass at the end. Now, some of the pieces were a little deformed where the zinc actually flooded in and I put a little too much. So there needs to be some more tests with that to make sure that I have the right balance of putty to metal, you know, what's the starting. So there needs to be some more tests, but I have been consistently applying it to some degree for my pieces. I just need some more testing to make sure that, you know, if I can get a proper liquid phase center, proper infiltration, and maybe send some tests. I don't have a microscope or anything like that in my garage, so maybe still need to send that over your way, Brad, to take a look at the microstructure to see what the actual end result of the center is. But like I said, most of these I do in a single stage. I do have some tests with the aluminum that I want to still try with some argon gas and inside some sealed containers, but we'll see if that yields any good results.
I'm confident that either you, me, or one of our users will crack the puzzle. It's a tough one, but it can be done.
I think it can be. It's it was frustrating it was a couple weeks, but it was a good frustration. If everyone knows the feeling, it's really being the pioneer, trying to just understand a material and you know, go at it head first. So it's like a good puzzle, and you know, I just love doing the stuff. So.
So Highball, you're providing an excellent example of the flexibility and control that this process offers. You're using your own printer, you're using your own kiln. You've even come up with your own ballast material that you're really liking to use. You've made your own crucible. So really pointing to the flexibility and control that the process offers and how you can affect every step of the process throughout.
Yeah, and having the recently, I'd say within the latter half of last year was when I upgraded to an IDEX direct extruder printer. So having the possibility of mixing materials, it was kind of like a thought for a while, and then apparently there were some researchers that actually did mix some different materials for alloying. But having the ability to mix something like copper with a ceramic or something, any of those pieces in the same print is not something that you can achieve with casting or with machining. It gives you unique possibilities for compound materials that I think, and for not that much. You know, my printer I have a 10-log TLD3 Pro, and you know, you can buy it on Amazon for $400 or so, and it's, you know, it'll get you to a point where you can print even just for the supporting with a cheaper plastic material. I can do overhangs and everything with cheap PLA. It pulls right off the copper, and you know, I can make some pretty interesting pieces, you know, with fairly low effort.
Yes, and thankfully you're showing us every step of every process via YouTube videos that are also entertaining to watch. So thank you for doing that. Look up Mister Highball on YouTube to see everything that he's worked through, including using that zinc paste, all of the processes that he used to get to this copper mask, including the fact that the nose is flat. And if you watch his video, you'll find out why. So really interesting stuff, really great work that you're doing. Thank you for helping us with the webinar today.
Yeah, thank you.
Thanks.
So we're going to start with what temperature is required to sinter and how much time is needed. So that is going to be material dependent, and all of the instructions that we have or the established processes are all listed out on our website on the page that's titled How to 3D Print Metal. So all of that is right there for you. It's like following a recipe. So the full instructions in nice detail are out there. How much weight can an unsintered part hold or support? And Brad, I'll let you take this one.
Are they referring to the green part or the brown part?
I would say the green part.
The green part, yeah. It's not, again, the general measurements don't apply. So it's a composite material. And we actually have very thorough data on our tungsten, because our tungsten, most of our users don't sinter it. They just use it with the plastic in it. And they're using it for radiation shielding or things where a great amount of mass is important. So if you go to our website and check out the tungsten, it actually has a full workup from a laboratory on all of its various strength properties. But generally speaking, it's difficult to break. I mean, it's easy to handle. Yeah, tough one to answer. Stronger. I mean, it doesn't have the properties of plastic. It isn't as malleable as plastic, as in it won't flex very far before it breaks, but it's much more rigid. And also it's highly resistant to abrasion, because if something rubs against it, it'll just move the plastic out of the way and expose the metal particles. So the wear, repeated wear, is just equal to the metal in question.
Okay, and a question that we get kind of regularly is, if your kiln doesn't go to the sinter temperature of the material that you want to sinter, can you simply hold it for longer at a lower temperature?
Right. The short answer is yes. The longer answer is it's tricky, or it can be tricky. And there's a few options here. If you go out so the science of sintering actually goes back to the 60s. I mean, it goes way back to the origin of ceramics, obviously. But as a science, powder metallurgy started taking hold in the 80s. So there's a tremendous amount of documentation on this stuff and methods of working with the material. Anything that's true of powder metallurgy in general is true of parts printed using our process. So there are literally dozens of encyclopedias on the topic that can help you bring this up to speed and help you refine your process.
And how about hipping, hot isostatic pressing? We have not done that directly, but we would love to. So if you have a connection to an organization that would be interested in trying hot isostatic pressing on these parts, we would love to work with them to do some of that testing. Brad, talk to us about residual stress and shrinkage.
This is kind of interesting. So residual stress in a powder bed laser situation, you're using a laser to heat up very small spots and then cool them down very quickly. So over the duration of a 12-hour print, for example, in a laser bed process, you wind up with a lot of internal residual stress, things where the part just wants to bend. So commonly they'll just take a whole part, warm it up, heat treat it, cool it back down to relax all of that. That is not a problem with our materials, and it's just inherent to the process. If it's properly cooled on the cooling side of the sintering effort, there won't be an issue with residual stress.
Okay, and the next question, what is the final inclusion particle size and percentage?
So this actually varies by material. Do you think they mean like the powders we work with?
That part I'm not sure.
Okay, well, I'll go with the powders part. So what is the final inclusion, particle size, and percentage?
Oh, I bet it's talking about the makeup of the filament and the material loading. So the particle size in the majority of our filaments, and I'll say, in the majority of our filaments is a -325 mesh. And the material loading in each of the filaments is different. So copper and bronze is around 90%. The steels are closer to 80%. The tungsten material, our rapid 3D shield tungsten filament is something like 94%. That's our highest loaded material.
Yeah, and let me clarify this topic in general. The numbers given are by mass, which for most applications really isn't terribly useful, but it's just kind of what the industry does. And it makes it easier for on the manufacturing side of things. In the end, if you look at it by by volume, there's a theoretical limit on how many particles you can pack into into a given area. And believe it or not, there's a whole mathematical study on sphere packing and circle packing and things like that. And I've done a deep dive into this. I've spent a lot of time on it. And there's a theoretical ceiling that's around 75%. So by the time you break something into little pieces and try to put it back together, you won't get to a filling by volume that is greater than 75%, I think is the number. That being said, our materials by volume also vary by the material, and they tend to vary where the ceramics, they'll only be about 50%, but our higher loaded materials will be up in the 60% by volume range, somewhere in there.
Brad, tell us about quality control standards and the filament manufacturing process.
Right. We source all of our materials like the powders and such. Okay, let me start with the polymers. Those are easy. There's really only one major manufacturer in the United States. It's NatureWorks. They make pretty much any PLA sitting on your desk. That's probably where it came from. Beyond that, we supply our powder materials from one of two places, either from the auto industry. The auto industry has a huge investment in powder metallurgy, and they've been doing this for 20 years. So it's an excellent source of high quality powder metal products. So some of our stuff we get from there. Some of the other materials we start with were originally destined for a powder bed fusion type environment with laser sintering or laser melting. So those are also incredibly high quality materials. Beyond that, on the manufacturing side, the size and percentage, we just mechanically measure it continuously. On the extrusion line, we have an automated laser micrometer that makes sure nothing is out of spec and such. And on the percentage side, we just do spot checks throughout the day and throughout the run.
Okay, a few more questions. Test results for traditional material sample tests. We don't have data on these, but we do have a group working on that right now. So hopefully into spring, we will be able to release some data. Now, this also is dependent on the process that you follow. How was your part printed? And then also how was it sintered? So we'll be able to return some data based on a specific process that was followed. If you follow that exact same process using the same equipment, you'll get the same result, right? But our process offers for you to use any equipment. It offers for you to have flexibility in every part of the process. So the data that we will be able to provide will be a benchmark, a guide. It won't be for sure this is what happens every time because of that flexibility.
Right. So this is going through a formal metals lab at the university. So we've very carefully recorded how we printed the parts, because we know how it's printed can have an impact on its final strength. So we've carefully documented that part of it, and we'll ship it over to UW-Madison, and then they're going to do the full line of metallurgical tests on it, everything you can think of, and it'll be to the ASTM standards. So this will be interesting, and it won't be the final answer because there's so many variables. It's only going to answer the question for parts that were printed in the way that we printed them and processed them, but it will still be useful information.
And that full process will be provided with that data as well.
Yes.
Now, do layer lines disappear after sintering? And I think the very exciting answer to this question is no, they don't. Right. And the reason I think it's exciting is because the sintered part maintains that level of detail. Now, you can file those layer lines out With the final part, you can do anything to that part that you would do to standard metal. So filing, sanding, to smooth those layer lines out if that's something that you don't want in your part.
Yeah, it keeps detail down to a fingerprint level of accuracy.
So what about supports and support material? If you have a dual extrusion 3D printer, you can use a separate support material, and that can be anything that you would use of standard PLA, including regular old PLA.
Yeah.
And PVA, that water soluble support material. If you have a single extrusion 3D printer, you're going to use more filament as your support material. All of those supports that are printed with your part are broken off, or they're removed, or you put your part into the crucible for firing. So we use that refractory ballast material to provide support during debind and sintering.
And in this is really interesting, an interesting side effect of the material. So metal is an excellent conductor of heat and plastic is not. And one of the key limitations of printing an overhang with a 3D printer is cooling the plastic. So what we've found is that you can get extreme overhangs with this material, more so than you could with plastic. So in this example, I'd always said I would never do a benchy, but I wound up doing a benchy. So this is the copper benchy, but this is printed completely without supports, including the bridge inside of the cabin and the bow. So supports are less important with this material. You can get greater overhangs than you could with plastic.
Brad, any experience with solar furnaces?
None.
Okay, that's a short answer to that.
That's interesting. I'd love to try it, but yeah.
Now, this next question was directed at Matthew. Talk to us about the minimum distance that the part should be away from the crucible wall to avoid decarbonization.
I don't know if there's just a minimum distance for decarbonization. I know you might want to put a minimum distance away just so that the effect of the heat from coming in from the sides doesn't affect the shrinkage. I found that when you have it in the center, the heat comes in from all sides, and then you get it uniformly hitting each side at the same time. But if you have it close to the wall, you've got heat coming in from the wall, but towards the center it's going to be cooler because the heat hasn't gotten there yet. But to actually deal with decarbonization is inner gas is great. Of like a furnace that you can put a inner gas through it is wonderful. But just having enough carbon where the carbon will be get taken away from the sintering carbon on the top, or extra carbon you've put within the furnace. Because once that's gone, then it's going to start taking from your part. Because the part's the hardest to get. It's all the way down, in the bottom of the crucible. But if you have enough carbon in other places that it can take from before it gets to your part, then that's perfect. And there's only as long as you don't open I've done that before, just to check on things, open the furnace, and then you're essentially resetting all the gases that are in there, and you're introducing new oxygen into it, and then you're going to use up more carbon. So as long as the furnace is closed, it will use up a certain amount of carbon, and then it'll you won't need more. So I think just having the most amount of carbon possible, and it will stop from taking from your part.
So let's stay on that carbon topic. We'll come back to that gases question after this. How do you control carbon content that stays in the part after debinding and sintering?
So I think what you're printing is kind of I'm assuming that's what you want in your part. If I'm printing the high carbon, I want to keep as much carbon in there as possible. I think if you print the part with the carbon content you want, and then provide essentially the furnace with more carbon than needed, it will take away the carbon from the carbon you've supplied and won't take it away from the part. So as long as you're printing with the carbon you would like to keep in the part, then that's the carbon content you will end up in the part, as long as you supply sufficient carbon.
Great, thank you very much for that. So talking about inert gases, the question is, have you done testing with inert gases? And I'm going to hand this over to Brad in a second, but I also want to tell you that we're getting a little bit of insider information from Paul here, because his question goes on with, for example, sintering aluminum in a partial hydrogen atmosphere, which will deoxidize the boundaries. So giving us that hydrogen clue again about sintering aluminum. So Brad, tell us about your work with inert gas.
First, I built a hydrogen generator. I haven't actually tried it yet, but I'm thinking the same thing. But here's how I've experimented with inert gases in the shop. Just simply, I put a heat tolerant tube in through the top of the crucible, into the top of the kiln, run it all the way to the bottom of the crucible, and then use the same ballast material, and then slowly trickle air up through it. I believe this is going to sufficiently displace any present oxygen. In the case of aluminum, the oxygen is bound up as an oxide, so it's more challenging. You have to remove what's already there. And this is where the hydrogen will do that. But there's obvious risk in dealing with kilns and hydrogen. So I will be going further down that path. And generally speaking, the testing that I've done with inert gases is, yeah, it's just a really simple way to replace the carbon that we're using now.
We did have one more question that didn't make it onto the slide, and that is about brass. Are we going to make a brass filament?
Yeah, here. One of our people here is kind of on a mission. He calls it his white whale. So we have a brass monkey. Yeah, we actually have a functioning prototype right now. And the main problem we've had with it is the filament gets brittle. But it doesn't do it on day one, and it can take a few days for it to get that way. And I know what's happening. The thermopolymers are depolymerizing, they're breaking down, but I don't know why it does it with brass and nothing else. So yes, we will do brass no matter what it takes.
Yes, so, and I chuckled a little bit at the question because around here, brass has become personal. So we are definitely on a quest to get that, and you will hear about it once we're able to get that out of the manufacturing machines. So that concludes all of our questions and our webinar for today. I want to thank you all for joining us today. Now you can continue the conversation in our Discourse Partner Innovation Forum. When you become a customer of ours, you become a partner innovator. So the very fact that you're buying this and working with it makes you an innovator, and we love to call you a partner as well. So talk with other partner innovators in that discourse forum and on Reddit. I know Highball's in there quite a bit, helping answer questions and talk through other folks' projects. Find our YouTube channel. We've got podcasts, instructional videos. Brad likes to put smaller science shorts on there. There's our LinkedIn page, our Facebook page. The instructions for everything that we've talked about today is at thevirtualfoundry.com/help. There's the list for our shop, and please always, you can reach out to us. So thank you all very much for joining us today. It was a pleasure, and Brad, I would be remiss if I did not ask you one more very important question before we wrapped up.
Let's have it.
What kind of fish do penguins catch at night?
I don't know.
Starfish.
Nice. A groaner.
Thank you, everyone. We will see you next time.
Thanks.
You're going to need to enable my video.
Okay.
Okay.
Yes, there you are.
Am I on? I can't see myself, so.
Okay, we're going to get to some questions. So I am going to, oh, that's not what I meant. Just a moment. Okay, we're going to display these questions here.